sure enough. So I will be recording this, and then so I'll post it if you have to leave a little bit early. Yeah, so we'll take a break at about 5 for a few minutes, let you get up, let me get up, get a drink of water. And then tomorrow we'll post our next quiz over 16.3 to 16.5. So all of the different integration there. And then I posted in D2L on the homepage in D2L, I kind of put at the top our updated schedule. So you can see that there kind of every day when you log in. I'm going to ask you to watch through 17.3 for next week, and we'll go over questions next week. And then I'll post the exam on next Thursday over 16.1 through 16.5 and 17.1 through 17.3. So let me start today with that email that you should have gotten from the college. So first of all, there is an extension to withdraw, and essentially they are being as liberal as they can. You can withdraw up to the last day of the semester, Wednesday the 13th. You can decide, you know what? Nope, I'm going to withdraw. I know that they are still considering an updated refund policy. Right now, like normally when you withdraw that late, there's no refund, but they are thinking about updating that. There's a no harm grading policy, and this is what I think people are most interested in and had asked about. So here's the grading policy, the way it officially works. I will just enter in my grades just as they are. I enter in my grades, and you can decide, you get to decide after the semester is done, actually until June 4th. Students will have until June 4th, you can pick this no harm grade, and that's a credit or no credit, but that's going to be your choice. You choose. This is for all of your classes this semester. And I think this would be most relevant if you were doing well and then kind of dropped a little bit. Maybe you were getting an A or B and then you dropped, you ended up with a C, and you don't want it to affect your GPA, but you still want it to count towards graduation. You can choose the credit option, just credit for that. For us, we talked about this, it's a little bit challenging because if you need Calc 3 as a prereq for another course somewhere else, then you need to be more careful with that. So that's really, you need to be really careful with that. I would be really, make sure I really was certain that either my degree here or where I'm transferring to, that credit for Calc 3 would be okay before I chose that. I have a couple of people who I haven't been able to get a hold of, and they've stopped attending. Normally, they would just get a failing grade, but there are no failing grades. Every F will be converted to no credit. So automatically, you're going to be converted to no credit. And then the D grades, that's where you could choose. You could choose, like if it's a class and a D, it's very rare. There's a few special instances where that could still count towards graduation. If it's a D, then you could take that. Otherwise, you can just choose, again, after the fact to call it a no credit, and then it doesn't affect your GPA. So it's going to be all your option. You're going to be able to make those decisions for any class that, if you happen to have a really short class that was done before we went, then that grade is what it is. But for all the classes that are still going, you'll be able to choose your grade once the semester is in, and you have until June 4th. They do ask you to, where does it say? They want you to meet with an advisor, like have a phone call with an advisor before you do that. I remember reading that somewhere. I can't remember where it is. But you have to actually have a phone call with someone so you kind of know what the consequences are of you making that choice. But again, I'm not going to worry about it. I'm just going to do my grades, and here's the grade you earned, and submit my grades, and then you'll have that option. I will have no part in that. You can decide. If you don't do anything, you'll just get the grades you get, and there'll be no change to it at all. So that's the official line. We had talked about that last time. We kind of knew that was coming, but now it's official, and you got the email. You should have gotten this email actually that evening, Wednesday, a week ago, like right after we hung up or whatever, right after we ended the meeting, you got that email. So that's what I know. I know about as much as you do. Does anyone have any questions about those policies, about the college policies.
So we're not forced to convert it to a credit or no credit option. We can still take it for the letter grade.
Yep, yep. And I know that's what a couple of people had worried about. Like, I need the grade. Maybe I need it to transfer, or I need it to count. And yeah, it's totally your option. If you do nothing, you will get the letter grades as usual. And you can do course by course even. It's not like I have to choose to do one or the other. You can choose, oh, for this course, I want the grade. For this course, I want the credit. Yeah. I don't know how that's going to work. I'm sure there's people, administrators and staff working hard behind the scenes, because that's like a new functionality that we don't have. So I don't know if you'll be able to do that, or if you have to just call someone and then they will manually do it. I don't know. I'm sure we'll get those details. Any other questions about that? All right. Just email me if you do have any other, or pop in the chat later if you want to. Let me pop over to the calendar again. So just to remind you, I posted this. I said I would get an updated calendar to you, so I posted this. It was like last Thursday or Friday, and I put it at the top on the homepage so that it's just its own little special thing there. It'll always be there. So we'll do a typical week this week. Next week, typical homework questions. We'll have an exam. Another week of typical. But then, like, I was like, what do we do finals week? Because Wednesday is the last day of the semester. How do we meet Wednesday and then have you turn the final in? I can't have you turn it in on Thursday because the semester is over. So I'm going to change the schedule a little bit that last week. We're going to meet Monday instead. We're going to meet Monday that last week. We'll go over homework questions. I'll release the final on Tuesday, and it'll be due on Wednesday. So we have to, just because the semester ends on Wednesday, we have to change during that last week. And I'll record again. You know, if you had set aside Wednesdays and you have to work Monday nights now because your schedule changed, it's not ideal. But yeah, so this is just going to be that change for that last week, because that's finals week. You will see, by the way, in some of the videos coming up, there's stuff where I'm like, okay, we're just going to skip this page because we don't have time. There's some proofs that we're going to skip. I did 17.3, you're not there yet, but I did 17.3 last night. There's a really cool physics example, why like energy is constant, but it takes like a 20-minute video by itself. I'm like, I'm not gonna make them watch that. So there's gonna be some parts of the notes. We're gonna I talked to one of my colleagues, Professor Wheaton. I don't know if anybody's had Professor Wheaton before, but he's taught this class many times, and he's like, yeah, maybe skip some of the proofs and then just do like a couple of examples near the end, and save the more complex examples, kind of skip those, and don't do any of those required problems for homework and stuff too. So that's kind of what we're going to be doing for the last 2 or 3 sections. Any questions about the plan now that we actually have one? Any questions about the plan for the rest of the semester? Okay, we have a quiz tomorrow over the rest of chapters 16, 3, 4, and 5. So what is that? Polar integrals, double integrals in polar coordinates, triple integrals, and then triple integrals in cylindrical and spherical coordinates. So it makes my life easier if we do them in order, so I can like go in each section at once. Does anyone, I've got 16.3 up here. Does anyone have, any questions, any homework questions from 16.3, double integrals in polar coordinates, that you wanted to ask about? You can type them or just unmute yourself and say out loud. I feel like I need more light. Oh, it's so bright in my face, but this is why I like film people. They have always bright lights. Like, it does look better. It's brighter. It was interesting. I was just reading this article. One of my colleagues shared it about like Zoom meeting, like not exhaust, like kind of exhaust, like just wearing out from all the digital meetings. And part of it is like having the camera on you. Like, I'd kind of start to get why people are like, I'm just gonna turn the camera off. Like it is exhausting to be on all the time, and so I get it. So any 16.3 questions? Not seeing any. We can come back to it if you have some later. How about 16.4, which is triple integrals? Anybody have any questions that you wanted to ask about from 16.4? Well, it's quiet tonight. So quiet, no questions. I don't know how to take that. I don't know. Does that mean like, yeah, I'm good, man, I'm good? Or does that mean I haven't started the homework yet? That would not be good. I understand how it's hard to keep on track and motivate yourself, especially when we're only physically, well, not physically meeting, but we only have a scheduled time once a week, but you got to stay on top of it. Okay, I'm not seeing any 16.4. We have lots of examples we can do, by the way. We have lots of examples we can do, so we will fill up the rest of the time, no problem. How about 16.5? That's cylindrical and spherical coordinate triple integrals. Any questions there? Well, maybe we just get to spend tonight doing lots of examples then. I'm going to pull up, you can still type if you need to, but I'm going to pull up, I uploaded, let's do 16.4, because we didn't do any of those last week. We did some 16.3, we did some polar integrals. There's only one that looks like that we didn't do, so that's pretty good. That's pretty good. Let's do 16.4. One last check over here. No other homework questions. Not seeing any. Okay. So I linked these from the home page here. I think we did most of 16.3, so we'll skip that. But 16.4, I'm going to do some of those now. So I have them loaded here. These are triple integrals. And so I just picked a few from the homework as some good examples that we could do as some practice together. So feel free. I know one of the feedback items was sometimes I can go a little fast, which is absolutely true. So if you go under, like you can just tell me you need to slow down or like type in the chat, but even if you just go under manage participants or participants, there's a go slower button that you can press. You can even tell me like, hey, a little like hint there, slow down. All right, so the first one here is just a triple integral. We don't need to do anything fancy. There's no drawing we need to do on this one. So this is just, let's see, we just have to remember we're integrating x first. So y and z are constant. So this is 0 to 2, 1 to 2, y and z are constant. Integral of e to the x is just e to the x from 0 to 1. Whoa, dz dy. And then we'll have e to, oh, careful here, don't assume the second one is 0, right? E to the 0 is not 0. Don't want to make that rookie mistake. So we have, I'm going to just put it out. Actually, we could just put it out in front, couldn't we? E minus 1, it's a constant, whatever that constant is. All right, so we have integrated x. Now we are ready to integrate z. And the y is still a constant, z squared over 2 from 1 to 2 dy. It's a little awkward there. E minus 1 integral from 0 to 2 of y times, let's see, z. It would be 2, right? 2 squared over 2 minus 1 squared over 2, so 2 minus a half dy. Oh, how am I going to fit this in here? e minus 1, and then there's another 3 halves being multiplied in there. Integral from 0 to 2 of y dy. So now I have 3 halves times e minus 1 y squared over 2 from 0 to 2. What a weird constant. 3 halves e minus 1 and then 2 minus 0. So 3 looks like 3 times e minus 1. Unless I've made an error in there, which is possible. Kind of resituate my computer here. One of these days, I'm hoping it gets warm enough where I can like sit outside and have class outside. How cool would that be? What some people like to do with these is they like to, I didn't leave enough workspace, but kind of do the middle integral like by itself and then pull it back in. And if that helps you stay organized, that's a really not a bad idea at all. What I mean by that is I'm gonna just mark some stuff in red. So if we look at this first integral, the integral from 0 to 1, y z e to the x dx, you could really just think of that as y z integral from 0 to 1 of e to the x dx, which is y z e to the x from 0 to 1, which is y z e minus 1. And then you can take that and then just basically plug it in to the double integral part you were before. And so for some people, it helps to kind of do that off to the side, do that integral, then substitute it back in. Then you have the next integral. I can't really label that one, but then you could do the integral from 1 to 2 of y z dz, kind of do that off to the side, get that result, pull that back in. So that's something that you could do. All right, any questions on that first one? Oh, I forgot. Did I not follow my list? I just forgot something. And I might have not put it on the list. I didn't put it on the list. We didn't go over your quiz. We did not go over your quiz. You should have your quiz results in the Dropbox, but I wanted to talk about them with you. I apologize for kind of jumping around here. Totally forgot about that. All right. First of all, the first question, there were like 2 snafus from me on this one. First one was that I had 2 pi r squared, which would be the surface area, that would be just the bottom and not, or like just, yeah, 2 pi r squared would be like just the hemisphere and not the bottom plate also, and it should be 3 pi r squared because it should include the bottom plate. So what I did for that, you get like impossible results if it's 2. So what I did is I just kind of accepted and gave you credit for it if you didn't notice that in time. So that was totally my fault. But with that, then it works out much better with the 3 there and not the 2. The key is to make a constraint function, and some people just use the surface area as their constraint function, and that's okay. It doesn't have to be equal to 0. But then you're setting the gradient of the volume function, the function, the optimization, the function you're trying to optimize, and you set that equal to the gradient of your constraint. And the key is the second component. When you let the second components, when you let the pi r squared equal lambda times 2 pi r, you get that lambda is 1/2 r, and then you can substitute that into the first equation, which looks really gross. 2 pi r squared plus 2 pi r h equals lambda times 2 pi h plus 6 pi r. But when you substitute in, it actually simplifies very nicely. You can distribute the 1/2 r. There's pi's everywhere, so you can divide by pi. What else here? Oh yeah, you have like terms, 2 pi rh, pi rh. And then you have 2 pi r squared, 3 pi r squared. That's where things get weird because if you have 2 pi r squared on both sides, it's just 0. And then you're like, well, then r and h are 0. How does that work? But if then you get pi r squared, and so that tells you that h is r, and h and r are equal. The way you do that is then you go back to your constraint, and you use your constraint to solve for r. The thing to keep in mind is once you do that gradient, the equality of the gradients, or the gradient, one gradient is a scalar multiple of the other, you have these two equations, 2 pi r squared plus 2 pi rh equals lambda times 2 pi h plus 6 pi r. And then you have pi r squared equals lambda times 2 pi r. And it feels like, how am I supposed to solve this? I have 3 unknowns in 2 equations, but you actually have the original constraint also. 2 pi rh plus 3 pi r squared equals 125 pi. So what you usually do is use the first 2 equations to try to get r in terms of h, or get h in terms of r. And then you use the last equation then to solve. And usually it involves solving for lambda. So that was the typical process there. The second example on the second quiz question was my second little snafu. And that was, I looked at it and I thought to myself, like, okay, you integrate, you get a natural log, that's fine. And I didn't do it all the way through. And the integral is like, it's really hard. I mean, it's not really hard, it's tedious. So you'll see here, first of all, the inequality 0 less than or equal to square root of x less than or equal to y means y is, if we kind of read it in reverse, y is greater than or equal to square root of x. So y is above the square root of x. So you're just in that little sliver there. So you have 2 options. You can integrate y first, and that's what I did here. You could integrate y first. So y goes from the square root of x up to 1, and then x would go from 0 to 1. And that doesn't look too bad because you have a y in the numerator and you have a y squared in the denominator. So you can do a U-Substitution. It seems to be pretty good. And you just get a natural log. And then you get here. And then I decided, oh man, because I don't know if you remember, the integral of the natural log of u du is u natural log of u minus u. And so I'm like, oh, that's gonna be a mess. So I said, okay, let me try the other way. Let me see if the other way is any better. And I'm like laughing because it was marginally better. If you do the other way first, if you do x first, now you gotta be careful. You gotta change your bounds. So let me show this one in red. If you do x first, x starts at 0 and ends at y squared. So x is going from 0 to y squared, and then y is still going from 0 to 1. And again, it's a U-Substitution. U is 1 plus x plus y squared. Du is dx, that's nice. So you just have du over u with this extra y hanging out here. So you get y times natural log absolute value of u, and you end up with this. And then I looked at that, I'm like, this doesn't look any better. But upon inspection, you actually have a y, and then inside you have a y squared, and same thing here. So I just ended up going with that one. I don't know if I could have just done the other one and it probably would have been the same difficulty. And that's where I'm like, maybe not a good quiz question choice, because this one is still a huge mess, and eventually I got the answer there at the end, and it was really gross. So
that
I tried
question was brutal.
It was brutal. It was not intentional. So I tried to be really liberal and give lots of partial credit, as long as you made, like, as your strategy was good, and not really take points off if you had like a sign error.
I want the ugly way. The first way that you showed, I want that way.
Yeah, and I think that probably would have been the same level of complexity at the end. I don't know that my way was any better. So yeah, not a good choice. Definitely not a good exam question. I will be sure to do them all first before I assign your exam and actually do them all the integrals through. We want to focus more on your setup, but we do want to have you do some integrals, but we'll try not to make them like this for the exam.
Okay, that makes me not worry too much because I thought to myself like, wow, these are quiz questions.
Right, right.
The exam is gonna be
right. No, that was unintentional. But that was my fault. I should have done it all the way through. The last one here was much more manageable. This would be a good exam level difficulty. We're just finding the volume under this surface, and it's nice because the region that we're integrating over is a rectangle. So you just pick either X or Y first, no big deal. I didn't even do the U-substitution here. If you integrate e to the negative x dx, you get an extra negative sign from the U-substitution. And when you simplify that, you get just 3/4. You just get 3/4, and then so you integrate the 3/4 y from -2 to 2, you end up with 3. And I did post this key. I did post the key. If you check in D2L, I think I linked to it in tonight's post in preparation for tonight. So that one's a little more realistic. That one's kind of the bottom end of difficulty for that section. We wouldn't see one easier than this. This is about as easy as we'll get, but it's like you gotta still know what you're doing. You know, it's not like it's a free point. So, all right. So that was a quick overview of the quiz from last week. I think what I might do, like a good level exam question from example 2, would be to write the second integrals, because some people struggled with these bounds. And so I think that's still worthwhile and a totally reasonable question to set up the bounds for that. And maybe I would just say, hey, do a double integral of some function, not even give you the function, and just say, set up the double integral with appropriate bounds and an appropriate dA. And so you would need to, like, if people struggled with the square root of x being less than or equal to y, it kind of threw people off. All right, any questions from the quiz? If you have any individual ones from your quiz, just shoot me an email and I'm happy to respond. I don't know, I haven't been doing any like office hours with anyone. So if you ever just want to chat about something, we don't have to do a video chat. We can do a phone, like we can just do audio, whatever, it's fine. But I'm happy to meet and kind of go over any questions you might have to go over your grading with you. I know, like I remember in my other classes, it's common for people to come up after they get their quiz back and kind of ask about number 2. Can you explain what I did wrong here? And because my writing, you might not be able to read it, but there might not be enough feedback for you to understand what you did wrong. And so feel free to just shoot me an email and we can chat about any questions you have. Okay, a little sidetrack there. Let's go back. We were doing some double integral or triple integrals here. Let's do some more triple integrals. This is 16.4 triple integrals. We're going to try to find this volume of the wedge bounded by the parabolic cylinder y equal x squared. Whoops, I'm still red. That's okay. So that's the back here. That's the y equal x squared. You can think of the parabola y equal x squared and then just extend it up. That's the cylinder. The planes z equals 3 minus y and z equals 0, which is of course the xy plane. You don't need to do this with a triple integral, but we're gonna use, notice the instructions, use a triple integral to find this volume. So you could do this with a double integral. You just integrate under the function z equals 3 minus y. So we're gonna do it as a triple integral. Here's how I think about these. I don't jump over to Maple. What just happened? Okay, so I think of a representative piece inside here. You have a little cube that's kind of inside your region. And we're going to add up in one direction or another. For me, if it's possible, it seems easier for me to add up vertically first. But kind of like the other integrals, you can add up x or y first. Here you have 3 choices to do first. There are 6 total possible integration orders. So, but I'm gonna do z first. So if I added that up, what I would get is a little like pillar. When I was done adding it up all the way from the top to the bottom. And so what I'm gonna do is I'm gonna integrate over the region dv. And in rectangular coordinates, the dv, I'm gonna do dz first. So z starts at the bottom, that's 0, and then ends at the plane. And so that would be 3 minus y. Okay, so now I have made this tall little pillar with my pen, right? So now I have 2 choices. Now I can add my pen up and get like a slice of bread or something in the y direction or in the x direction. I'm just gonna pick the y direction next. I don't know that one is easier than the other, but what I would get is like this kind of angled slice. Can you see that in my terrible drawing? Oh boy, nope. This needs to go all the way and kind of touch with that. So you'll get like this slice, right? You'll get a whole, it'll end up being like a triangular with kind of a curve on the back, because the back part of it is on the parabola. So I think I need to look at that from above, because I can see that y is going to go from the parabola to whatever this ending y is, whatever that ending y is. So I think I need to look at this from above and look down on the xy plane. I don't know. I feel like there's some spatial reasoning that for some people is easier than others. This is where like I'm happy that my kids like Legos, because a lot of those instructions you have to like kind of picture you're looking at it from the back or this side, and like it kind of teaches you good spatial reasoning, because I need to know where this ends. And then I have y equals x squared here, and here's the region I'm looking over. And I don't know if you can see my slice. My slice looks like this, if just from above. It goes from the parabola all the way out to whatever that value is there at the end. So I think it's pretty clear if I add up y next, y goes from x squared, that's the parabola, up to that ending point. So how do I get that ending point?
You plug in 0 for the plane of z equals 3 minus y.
And just to be clear, because I know you know, but just for everybody else, where do you plug in the 0? For what?
Z equals 0.
Correct. So everybody see that? So right here, z equals 0, and so we'll set that equal to 3 minus y, and so that means y is 3 there. So y goes from x squared up to 3. This is my new favorite thing to do. I don't know how I'm going to go back to writing on regular paper, because I can like, well, I kind of ran out of space. Oh, that was not good. What happened there? Why didn't it just let me grab that? There we go. So you're like, well, I ran out of space. Let me just move it over here. I don't know how I'm going to go back to regular paper. Okay, then we have x, and this is where I'm going to look at it from the top again. And I just have to figure out where does x start and end. By the way, if you're thinking of using symmetry there and doubling those, that's a great idea. We don't have to do it, but it is a good idea. So, how do we figure out where x starts and ends? It's obviously negative something to positive something. It's symmetric, but how do we figure those?
Use x squared equals y? No.
Yes, partially.
Now that we know that our endpoint for y is 3, we plug that into y equals x squared.
Right, everybody? So we want to know where those intersect. That's exactly right. And so x is equal to plus or minus square root of 3. So negative square root of 3 to positive square root of 3. And again, I think an exercise like this, even just setting up a triple integral that would find the volume of the wedge bounded by blah, 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 is a really good exam question. So let's pause there. Are there any questions right now? Okay. Let's go, and I'm just going to go in line here. And in the next step, you will see why we could have done this as a double integral. Because we integrate dz, that gives me z from 0 to 3 minus y. Then we have dy dx. And that's the integral from negative square root of 3 to square root of 3, integral from x squared to 3. And that'll just give me 3 minus y minus 0. So just 3 minus y dy dx. And if you look back at the examples that you did in, this is actually right now, it looks like a section 16.2, where you're finding the volume under a surface over a non-rectangular region. So you don't need a triple integral to find this volume. Okay, then we'll keep going. Integral negative square root of 3 to square root of 3. We'll integrate that dy, so that's 3y minus 1/2 y squared from x squared to 3. This one's going to be a little messy here. It's going to be polynomial, but it's going to be a little messy. Negative square root of 3 to square root of 3. Let's see. 9 minus 1/2 times 9 minus 3x squared minus 1/2 x to the 4th. I think that looks okay. I'm going to simplify our lives because the volume is symmetric. I'm going to double because then I only have to plug in 1 square root. So I'm going to go double from 0 to square root of 3. And let's see, 9 minus half of 9 would be half of 9. So that's 9 halves minus 3x squared plus 1/2 x to the 4th. I think I'm okay there. Any questions so far? We did z and then we just did y. Any questions so far? Okay. All right, let me go over to the left. I kind of want to just distribute the 2. That's okay. 2, 9, yeah, I want to distribute the 2. So we'll call it 9, and then it'll be an x because we integrated, minus, oh, distributing the 2 is a bad idea. Trying to do this all in my head. Let me distribute the 2 first. That'll just be better. 9 minus 6x squared plus x to the 4th. No integration yet. So I distributed the 2 to make our lives a little bit better. Okay, so then 9x minus x cubed over 3, so 2x cubed, and then 1/5 x to the 5th, all from 0 to square root of 3. And we get 9 square root of 3 minus 2 square root of 3 cubed plus 1/5 square root of 3 to the 5th. Minus 0. Square root of 3 cubed. Well, 2 of those will make 3, and 3 times 2 is 6. Okay, there's an extra square root of 3. Similarly here with the square root of 3 to the 5th, square root of 3 to the 4th will be 9, and then there's an extra square root of 3. And now I am too lazy to do the fractions. It's 3 square root of 3 plus 9/5, 15/5 plus 9/5. 24/5 square root of 3. I should have the right answer so you know that we have it right. This is when I get overconfident. I'm like, oh yeah, I can do that in my head. And then it's not right sometimes. But I can cheat because I have the answers. These are from the homework. So we can make sure we're right. Oh. Let's see, 16. Any questions on how we finished that one up?
Isn't the integral supposed to be from negative square root 3 to root 3?
Yeah, I kind of, what I did here to make our life a little bit simpler is I noted here, can you see if we cut this in half? Oh, that's a terrible line. It's supposed to go all the way down to the y-axis. If we cut it in half, it would be in half. The two halves would be equal. And so if you look at it from above, if we cut it in half, we really can just double the right side.
Oh, that's how you got the 2.
So that's where the 2 came from. Yeah.
Okay. Okay.
Yeah. I could have done it early on. I just thought, oh, it won't matter. And then I got to the point where like, well, I don't want to plug in square root of 3 like twice. So that's why I changed my mind there. Oh my gosh. Got like warning bells going off. You can't hear my system audio, can you? Because there were just like 6 warning bells going off there. That's good.
No.
Okay, good. All right. I just want to make sure. I hate like giving you bad information here. So what is this? 16.4, number 20, I believe. Sweet. Come on. Come on. There we go. Yay. Success. All right. Okay, let's move on. Ooh, this one is interesting. The last one, this one would be hard with a double integral. Pretty challenging. So I guess we're going to do a triple integral again. We have to think of our representative piece. Whoops, I guess I'm doing red now. And we have to pick a direction to add it up. We have on the back, kind of out of our line of vision, is y equals z squared. So what that is, that's the cylinder, y equals z squared, y, z, and then you kind of extend it out. So that's what you're looking at there is like that parabola that's been dragged along the x-axis, and it's just a little snippet of it, y equals z squared. And then we have z equals 0, x equals 0, and then this plane z equals 2 minus x minus y. So there is definitely a direction that is the better choice here. I do not think it is going to be clear to students. So let me see if I can I draw these quickly in Maple to get us an idea here. So let's do that. Let's do with plots, and let's do display. And we want to do plot 3D, no, implicit plot 3D of, what was it, z equals y, no, y equals z squared. And let's go x equal, I think maybe we just do that. Surface color equals blue. Let me see if I can graph that first. Implicit plot. Oh, so I have to give the, okay, x equals -2 to 2. Actually, no, just 0 to 2, right? 0 to 2, y equals, we can go 0 to 2, z equals, we can go 0 to 2 on all of them. Okay, all right, so there's that. And let me go X equals normal. Okay, so there's that one. And then let's do plot 3D. And it was z equals 3, where did it go? 3 minus 2 minus x
minus y.
Thank you. 2 minus x minus y. X equals 0 to 2, y equals 0 to 2. Style equals surface. Color will make this one red, and I think that should do it. Whoa. Whoa, we got like, okay. And let's, I'm gonna try to cut this off. View equals, I just want to cut it off at the XY plane. Okay, so here we have it, finally. The blue is z equals y squared, and you can see the parabola there. There's the y-axis. The red is the plane, and so we are looking in this little corner down here in the bottom as I've rotated it. I'm kind of looking at it from behind, from the picture in the notes. So we have to figure out, here's why I wanted to draw this. We have to figure out a direction. Do we want to add up in the z direction first, in the y direction first, or in the x direction? And so I definitely have a thought in my mind what I would do first. I think there's one good plan, one okay plan, and one bad plan. Does anyone
with the DC first?
The z that's the bad plan. Sorry. Does anyone know why starting with z first is challenging?
Because the endpoint is the intersection.
The end. Could you explain that a little bit more in depth, Jacob?
So from z, you start at 0, but as you add up going up,
Yep.
you don't have like a closed off point.
Mm-hmm.
I don't know how to explain it too much,
Yeah.
but
Yeah, I like it. So think about if you're over here. Did I tell you, by the way, that I discovered I can annotate while in Zoom? I can like write on the screen, and you're adding it up vertically this way. That's like a terrible thing, terrible drawing there. But you go from the plane up to the plane. But if you add it up over here, now you're going to add up, and you're going to go from the plane, the XY plane, up to the paraboloid, or the cylinder. Excuse me. It's a parabola, but it's not a paraboloid. It's a cylinder. It's a parabolic cylinder. And then that's going to change along this intersection is somewhere in here. There's this where it switches from being one to the other. So I don't know if you remember finding areas between curves, and if you have like a function like this and a function like this, you could go x and add them up across, but you'd have to have two integrals. It might be easier to go y first, because then it's just the same on the left and right the whole way. So that's essentially what's happening here. And then I can clear all drawings. That's so cool. Okay, sorry. So I like, my kind of default is z, because that's what I'm most used to. But I think going z first in this particular example will be difficult, because what Jacob's saying there, that it's not going to be the same lower and upper. There's that intersection along that kind of spline that makes things more difficult. So does anybody have a preference with x or y next? And I think either will work.
would x be easier because if we're not using equations, we're using like concise points?
Yeah, I like x first myself as well. So let me rotate this a little bit. I have to turn off the annotate so I can actually look at this again. And I like x because when I'm adding them up, I have my little representative piece. I'm adding them up all the way from the YZ plane all the way out to this red plane. And that's the same all the way down to the parabola, because the parabola is parallel. And so you're going directly with it. So the parabola really doesn't get involved with the x as you go in and out on the x-axis. So that's how I would do that one as well. But you could do y first. You definitely could. So we're going to go back to this. Let me see. Now I'm switched around. We decided we were going to add out in the x direction. Okay, we're going to do the x first. Okay, so we're just adding up, again, we're finding the volume, and the volume is just the integral over the region dv. So the argument, the integrand, is just going to be dx and then dy dz or dz dy. And x then starts at 0. Whoa, gosh, I keep doing that. Starts at 0 and then ends at the plane, I guess. It ends at the plane. But x can't end at 2 minus x minus y. That doesn't make any sense. It has to be when x ends. It has to be x equals 0 and x equals, because they're x values. So how about somebody who hasn't answered yet today? Do you know what I'm hinting at there? What we're going to put for that upper bound, or how we're going to find it? Zubes is right. Zubair is right. We're going to solve for x. That's correct. Oh, I think I have like the touch mode off or something, because every time if I touch the screen with my, rest my forearm on it, then I'm like hitting other programs. So if we solve for x, I'm just going to add x and then subtract z. So x will be 2 minus y minus z. And that is a perfect example of why I draw the lines through my z's, so you can tell that they are not 2's. Or I say it so I can tell that they are not 2's. Z would not be 0 there, no. Not, because it is, whoa, I don't know what is happening tonight. There's I've changed some settings or something. But we're along this plane, and so Z varies. It definitely is not always 0 there, no. It's only 0 on the XY plane, but we're adding up. We need to add it. That's why I picked a little cube in the middle there and kind of added up in the middle. Z is definitely not 0 there. Okay, so now we need to decide, do we want to add up in terms of Z or add out in terms of Y? And I think it's the same thing. Z is going to be hard. Z is going to be hard because it's going to be because of that intersection up at the top. So let's do Y next. Christian, did you have a were you going to ask something? No? Okay. All right,
No,
now
I was just gonna say to just go through Y.
Mm-hmm. Yep. How did you know? What was your reasoning that you thought, let's do Y next?
Just like you said, C is not 0, so you probably have to figure out a different variable first in order to get back to Z.
Mm-hmm.
So,
Yeah, that makes sense. So now what we're going to do is we're going to add, it's going to end up being this weird slice. That's probably not what it looks like. But we're going to add up and add these all the way along the y-axis from the parabola. Ooh, that's helpful. From the parabola to oh, kind of, yeah. We almost, I think what I want to do is, so we have Y and Z next. So I think what I want to do is I want to look at it from the X. I want to look at it from this direction.
well, you have to set X to 0 and the Z equals 2 minus X minus Y.
That's kind of what I was thinking. I want to look at the Y Z plane because we've integrated X. So we're done with X. And so now we're really just looking at this region in the YZ plane. And I think it was Jacob who spoke up earlier. You're right. You're absolutely right. Because now we're adding up in the Y direction, and we're going from the parabola, where Y is equal to Z squared, to the plane and this is where Christian's also correct, it's the plane, but it's when x is 0. Right?
Yep.
Or, yeah. God, I'm like a moment of panic here.
So it would be y equals 2 minus z, I think.
Mm-hmm. Yeah, we can't have an x in there because we've integrated the x on the previous step. So you can't get an x back in there and have an x in that bound. Okay, and then finally we'll have dz, and that will go from 0 up to, I guess we have to figure out where they intersect.
Again, use y equals 2 minus z, but set y to 0 because you're already done with y.
Yeah, but
So,
y isn't 0 here. Right, it's
yeah, that's right.
right? But it's the intersection of these two curves, y equals z squared and y equals 2 minus z. So I think what we want to do is we want to set those two curves equal to each other. Oop. And then we can solve that algebra. Let's see, z squared plus z minus 2 equals 0, z plus 2, z minus 1. And so z is equal to -2 or 1, but -2 would be down below. We don't care about that one, it's 1. So z will go from 0 to 1. Okay, so I think we're pretty good. Just gonna check to see if we had the same thing. We'd have to wait until we get an answer because they did y first instead of x. So we can't check with the solutions manual. We could check the final answer, but I think we'll just pause right here and see if I don't think we have time or space to actually do the full integral. Anybody have any questions about the setup for this one?
No, not me. Well, actually, yeah. Well, how do you know which to go from on the z, from which one goes on top and which one goes at the bottom? I keep having a little confusion.
Mm-hmm.
Yeah, which one goes where?
You're going from least to greatest on all of these. You're always going from the smallest one to the largest one. Whether it's negative or positive, you're going from the most negative to the least, whatever.
Yeah.
So the z, you're just adding them up vertically. So you're going from the xy plane where z is 0 up to when z is equal to 1.
Okay. I understand that now.
Okay. Any other questions? Okay. That integral is just polynomials, so I think our time is probably better spent on setting another one up. So I'm going to pause. If you are interested in trying this one out, it should be, if we get the same thing as the textbook, you should end up with 17/20. So hopefully we set that up right. It looks good to me, but you never know. I never know for certain, but it looks pretty good. Okay, so let's see. Oh, this is kind of boring. Just an integral. That's good practice though. This one is not over. The first one that we did was over a rectangular region. The bounds were all just real numbers, and this one is not. So let's try that. Is that the last one? Oh, this one's more interesting. Yeah. So let's do, oh, it's almost time for a break. You know what? Let's skip and do 48 next, because I want to get into 16.5 after this for sure. So let's do 48. And all we're doing is changing the order of integration here. Then we'll have a little break, and then we'll come back and we'll talk about 16.5, some triple integrals in cylindrical and spherical coordinates. That'll be good. So let's do this 48 here. We're going to change the order. And so for me, the only way I know how to do this one is I have to somehow draw the region and figure out the region. I am unable to just change the order with some algebraic manipulation. So what I need to do is I need to kind of label these. These are z values here. So z, let's see, y is positive and negative. X only goes from 0 to 1. And we don't go below the xy axis because z starts at 0. Okay, so I'm just drawing my coordinate axes here. So z goes from 0, that's the xy plane, up to the square root of 4 minus y squared. So I guess we have to wrap our heads around what is that? The square root of 4 minus y squared.
Is it a semicircle?
Yeah.
Yes and no. It's a semicircle if it was a function of two variables, but it is technically a function, or sorry, if it was z as a function of y, but we're in 3 dimensions. So it's the 3-dimensional semicircle thing here. And the key is that,
So it's half a
hemisphere?
cylinder then?
no, close. It feels like it should be a hemisphere. It is not though. It's
Half a cylinder?
Yeah. So if you look at the cross section, z is square root of 4 minus y squared, and that's the semicircle you were thinking of, which is great. But that's only when x is 0, but it doesn't tell us what x is. X can in fact be anything, and so you can think of that semicircle pulling out along the x-axis. And so that was not good. They didn't look like the same size at all.
It's half a cylinder.
Yeah. So it's like it's been cropped, not just because of my drawing, but it's been chopped, right? It's the top half. And in fact, we can tell, where does it end?
It ends at 2.
Close. Good idea, but not 2. Those are y values.
Oh, it ends at 1.
At 1. These are the x values. X ends at 1.
Oh yeah, I just noticed that.
Yeah, it's okay. It's okay. How about somebody else? What are the 2's? Where are they involved? They're kind of implied, but where are they on the picture? Yeah, the thickness. Yeah, the width, right? Right. This is -2 to 2. So we didn't really even need to know that. That was kind of implied that z was going from 0 to the curve, and then x goes from 0 to 1. The -2 and 2 kind of just, well, they have to be -2 and 2. Unless you only have part of it, I guess. You could chop off the edges or something. Okay, so we want to now have our little representative piece in here. I should do a different color. Oops, and I just took out my y-axis. A representative piece. Now we want to add in the y direction first, like so. So we're going to go, this is weird. We're going to go from the semicircle, right, from the cylinder to itself. Ooh, let me look at that from the side. So let me look at, I'm going to pretend that the x-axis, this is like the xy plane as my horizontal, and then the z is here. And I'm looking at like down the x-axis. So this is, I guess I could just call this the y-axis here. And I have this semicircle. And this is z equals square root of 4 minus y squared. But I'm going from that to that. Yikes. So I need to have y values there for that first integral. Oops, that's not enough space. I need to have y values there. So I really need to solve for y. If I square both sides, z squared equals 4 minus y squared. y squared plus z squared equals 4. That's the full circle. And if I solve for y squared equals 4 minus z squared. Y is the square root, actually plus or minus the square root of 4 minus z squared. And what that is, this is y, my brain wants to do x, y and z, that's the right half and the left half. Now we don't have all of that on our picture. We just have the top little quarters. But here's y equals square root of 4 minus z squared. And this one is y equals negative square root of 4 minus z squared. So when we add up y's, y actually goes from the negative side to the positive side. Negative square root of 4 minus z squared to positive square root of 4 minus z squared.
With what we did earlier, could we write 2 times the integral of 0 to the square root of 4 minus z squared?
Yes, absolutely. Yep, absolutely. Did everybody catch what Jacob was saying? Because these are symmetric, if you slice this guy in half, it'll be the same volume on either side. So you could just find the volume of the right side. Just that volume over there.
And then multiplying it times 2, right?
Double it, and then double it. Yep, good idea. I like looking for that whenever you can. Simplify your life. Okay, now we need to add z. And so z, we've done the y. If you look on the red drawing in the middle, we did y. Now we're going to add up z. That's just going to go from 0 all the way up to the top there. 0
to 2?
2, just 0 to 2. Yep. It feels like, oh, it's going from 0 to the semicircle. But remember, we already took care of the semicircle. That was addressed in when we integrated y. And then we add them up in x. And then the x will just go from 0 to 1 again. Yeah.
That was simple enough.
Yeah, it's the first one that requires the most work usually. Maybe the middle one, but then once you get to the last one, that's usually the easier one. If you think of on the original picture, we're adding the y's first, then we're going to add the z, and that's where we end up with, like, you can imagine slicing the loaf of bread or whatever. You get like a little slice. That looks terrible. Anyway, there's a slice there, but then you're adding up the slices along the x-axis, so you just add them up, just 0 to 1. That's it.
So if we're finding the volume of a shape, will the last integral always be in terms of constants?
It must. That's correct. It's a red flag if you set up your triple integral. In fact, even a double integral. Some people did this on their quiz and then they got lost. If you're finding a volume, your outer integral cannot have any variables in it. It must be constants on those bounds.
Yeah, or else you wouldn't get an answer. You still get more variables.
You'll get a function. That's correct.
Yeah.
Yep. Now, that's just kind of a check. That's a red flag. It doesn't mean your answer is right just because it has 0 to 1 there. But if it doesn't have 0 to 1, then you should be like, whoa, hold on. This can't be right. Something is wrong here. So it's kind of a good check. It's a good point, Jacob.
But the middle integral can have variables.
Correct. Yep, these did not. This one did not, but I think our previous, this guy did, right? Yep. Yep, so the middle one certainly can. Good questions. Any other questions on that one?
Nope.
All right, I'm not seeing any in the chat or no hands raised. So
If we were to solve
ahead.
for the whole cylinder, then for the second triple integral that we set up, it would be from -2 to 2, right?
Correct. And you could double it again.
Or yeah.
Right? So either way would do it. And then the Go ahead.
Yeah. The first one would be from negative root 4 minus y squared.
That's correct.
Or we could just double that too.
Or you could double it, yep. So if we wanted to do the full cylinder, we would go from negative square root of 4 minus y squared. Or if we were finding, I'll give you just a little joke before we go. The most efficient way to find the answer to this question would be to use the volume of a cylinder, pi r squared h, but we have half of that. If we can, so that would be much more efficient to just say 1/2 pi, the radius is 2, the height is 1. There's your volume, 2 pi. All right, so let's take a 5-minute break. We'll come back at about 5:17-ish, something like that, and we will work on 16.5. If you want to download that, it's linked on the homepage in D2L. Some 16.5 extra examples. Yep, I'm still here. 16.5 extra examples, and we'll do some of those in about 5 minutes. All right, see you in a bit. All right, I'm gonna try these headphones instead. I feel like the Beats ones are nice, but I feel like they make me talk loud or something. I don't know. It's just weird because I can't hear everything. So then I'm like talking extra loud. So, I don't know. I'm gonna try these just regular cheap ones. We shall see. Okay, so we're going to jump in and do some triple integrals here in cylindrical and polar coordinates. Before we do, did anybody have any questions you wanted to ask before we jump back into it here? No? Anybody have like super exciting dinner plans tonight? No? My wife's doing, we do the HelloFresh. We do like 3 or 4 of those a week, which are nice, like because we are not really great cooks and they tell you
I love
exactly what to do.
HelloFresh.
It's good. Yeah, we're doing like this burrito bowl or something tonight. So, yeah. Do you do that in your family too, Jacob?
I used to do it myself just because everyone was pretty busy, so I would just like cook myself at home.
Yeah.
But now I'm with my cousin right now in
Okay.
Las Vegas,
Okay.
and like once a week we've been cooking Filipino food,
Nice.
so that's been fun.
That's cool. And it's definitely like there's some stuff in there where I'm like, man, I could just go buy this stuff. But there are plenty of meals where it's like, you know, it has like 1 jalapeno pepper and 1 like stuff where it's like I wouldn't
And you
have
have to
just
buy it
that.
in bulk at the store.
Yeah, so it's kind of
Yeah.
I like it. I do feel guilty about all the waste with all the packaging, but all right. Anyway, back to more interesting things here. So let's take a look here. One of the things I find when I'm doing the cylindrical coordinates is it just feels like I'm doing a polar integral because that's kind of what it is, right? The cylindrical coordinates, when you do them, you're doing this triple integral. Oops, I'm in red here. So you're doing this triple integral and your dv, and it's just dz and then polar, r dr d theta. So for me, it really just feels like I'm doing a polar integral. And I don't even think of it as cylindrical coordinates, even though that's like the technical name for it. But really, it's just like you're doing that. And the way you're going to notice that is, like you can see here, the name of it, cylindrical coordinates. Do you see what we have here? The cylinder, right? So if the region that you're integrating over is a cylinder, that's pretty much the only time you're going to use cylindrical coordinates. Or like, and I don't mean the whole thing doesn't have to look like a cylinder, but if you look down on the XY plane and it's circular, that's the red flag. That's not a red flag, it's not bad. That's the sign that you're going to do cylindrical coordinates. So let's do this one here. And here's how I would do this. We actually did some of these back in section 16.3, where we did them as like triple integrals. And we just kind of did the first integral. So let's see, I guess that 1 over x squared plus y squared would just be constant. And we're going to integrating dz, so it would be z from 0 to 2. And then it's dy dx. So I'm not doing anything cylindrical yet, no polar. I'm just integrated dz, and that's z from 0 to 2. And then I have this -3 to 3 integral 0 to square root of 9 minus x squared. That's just going to be 2 over 1 plus x squared plus y squared dy dx. And then now I'm just going to say like, well, hold on. That's a semicircle. In fact, I drew it up here, right? In x and y, it's radius 3. Y goes from 0 up to the circle. That's y equals square root of 9 minus x squared. X goes from -3 to 3. Well, then why don't I just switch to polar? And that's essentially what you're doing when you're doing a cylindrical coordinate system. You're just switching to polar. So now we're going to switch to polar coordinates. X squared plus y squared is r squared, and dy dx becomes r dr d theta. And I think it was Christian asking about this last week or the week before. There's always that r there. It's just part of the dA. dA is either dy dx or r dr d theta. The r is always in there. And then now, instead of my complicated 0 up to square root of 9 minus x squared, r just goes from 0 to 3, and theta goes from 0 to pi. Now we've converted it. Now it's a cylindrical, really all we did is a polar conversion, right? But now we could think of it as cylindrical coordinates.
If we wanted to keep the dz, would we have to change anything else when we're translating it to a polar coordinate integral?
If you wanted to like convert at the very beginning, you mean? And
like if we wanted dA to be dz r dr d theta?
Well, you're thinking dv, right? If you wanted the dv to be dz r dr d theta, it can't be dA because that's area. I think I know what you mean. Let me come back to that. Let me do it off to the side. So we have this triple integral, and it's 1 over 1 plus x squared plus y squared dz dy dx. So you can convert right then if you want to. The challenge for me, this is more for me, is I struggle with the bounds. I find it easier to do the bounds once I know what my region is in the xy plane. And you can do that there. Well, it's z from 0 to 2, so z would still be 0 to 2. And then I just have to convert those x's and y's to r's and thetas. But you can do it, I don't know if this is what you're asking, Jacob, but you could do it right initially.
That's the form I was looking for. Or the form I was asking about, I should say.
Yeah, you can definitely do that. Yeah, for sure. A lot of this becomes, personal comfort level and your familiarity with it. And I tell my students that last fall I taught Calc 3 for the first time. It was really fun. It was a challenge teaching a new course for the first time. It always is. But one of the special challenges for me with Calc 3.
What do you usually teach?
Usually the calculus sequence. I've taught differential equations before, past this, and then I do lots of stats and algebra.
Are you teaching that class during the fall, by any chance?
No, we have, that one's in high demand, so is this one. So we have like 4 or 5 people that want to teach it, and we only offer like 1 or 2 a semester. So we have kind of a rotation, yeah. Though I do have seniority and I could just teach it every time if I want, but I'm too nice.
Okay. Yeah, because
yeah.
I'm trying to see if I can take either differential equations at Elgin or maybe at the Page, because I know Aurora is only going to have the morning class.
Gotcha. Yeah, we usually do have one at night.
Yeah, that's what I'm looking for.
And I don't know, Dr. Campbell might teach that at night.
Are they usually like multiple times a week or just 2? The usual 2?
Two. Yeah, it's usually 2. During the day, because that one's 4 credits now. So the ones that are in the late afternoon, evening would be 2 days a week, and the other ones are 4 days a week. Yeah, because there's usually like a 2 p.m. or a 10 a.m. There's like something during the day too. Yeah. But this is interesting. So for me, the math that I had after this as part of my undergraduate degree, which was math education, and then in my graduate degree was applied and computational mathematics. I had a stats emphasis. I did some modeling. The only triple integrals I have ever done were in Calc 3. And so before last fall, the last triple integral I did was in 1994. And so some of this is like, well, from my experience, it's easier for me to do the DZ first and then convert to polar. I mean, your comfort level might be different the more of them you do, and my comfort level might change, the more of these I do. So that's all personal preference. That was the long way of saying that it's personal preference. Okay, so now here, this is a nice easy one. There's a nice U-substitution we can do here, 1 plus r squared, and it's actually perfect. du is 2r dr, so I'm actually not going to do the substitution and just say, well, that's du over u, that's just natural log of absolute value of 1 plus r squared from 0 to 3. If you forgot the absolute value here, you'd actually be fine, because it's not necessary, because we don't have any negative arguments there. 1 plus r squared is never, it's always positive. So you don't really need the absolute value there. And that's just the integral from 0 to pi, natural log of 3, no, natural log of 10, excuse me, minus natural log of 1. But everybody knows, right? Everybody knows the natural log of 1 is 0. Thanks, Jacob. Yep, everybody knows that one. So then we just have natural log of 10. So that'd be natural log of 10 times theta from 0 to pi. So we get pi times the natural log of 10. One thing to note here, when we get to this exam, I am not going to assign you a coordinate system. So on this one, I would just ask you, find the volume maybe, or evaluate this integral.
Oh, so you're not going to ask find the polar, evaluate using polar coordinates?
I am not. Nope.
Okay.
So I want you, the only reason we study polar coordinates and we study spherical coordinates,
To make it more simpler.
correct. And so that skill is only valuable if you recognize
yes.
when it would make it simpler. That's the only way that skill is useful. So I'm not going to tell you when to do it.
Okay, but a quick question about the final. Are we just doing 17, chapter 17?
Here's the way the final is going to work. We will probably, so the final will have some chapter 17 questions on it, more chapter 17 than the other sections, but
Okay,
the
so
entire
cumulative.
course, it is cumulative. It is cumulative, but it'll be like, think of a final. It's a little bit longer than a regular exam, a little bit longer, because I know Professor Teichert would have given you a little bit, like about half your class period. So the final, you would just have the full class period. And then we won't have a test on that chapters 17, the 17, 4, 5, 6, 7, and 8. We won't have a test on those. So those, I'll try to put as much of that as I can on the final. And so that stuff will be on the final. Probably won't all be there because there's too much for it all to be there. And then the rest of the chapter will just be like little snippets, because there's no way you can do the whole, even the last test was just snippets of chapter 15. There's too much. So I think I will ask Professor Teichert for his old exams, or if somebody wants to just email me theirs. What I like to do on the final is I like to focus on what are the big picture concepts, what are the main ideas from this course, and focus the final on those. And the reason why I'm thinking about old exams is if it's one of the big ideas, it should have been on an old exam. So the idea of what we're working on in chapter 15, it's all like the partial derivatives. You need to be able to find the gradient. You need to know what the gradient means. So that should be on the final, that kind of thing, that it's like the gradient is a big idea. And so that, so when you're studying for that and thinking about the final, I'm not going to really focus on some little minutia idea that was maybe one page of your notes, or was like one really hard example at the end of the section. Like that's not really what a final is.
Like finding the normal vector of all that.
Yeah, right. So find the tangent vector, find the speed of the object if it's moving along this path. Oh, that's the magnitude of the velocity vector. So, big picture stuff like that is what's going to be on the final. But some of the final will be new stuff from the last few sections of chapter 17.
Fair enough.
Yeah. And as a reminder for anything, if you missed it earlier, we're going to do things a little bit differently that last week too. Because I don't want
we're doing a Monday class instead of a Wednesday class, and just
because the semester ends on Wednesday. I don't want to have our class talk about some questions and then say, hey, okay, you have 6 hours to do your final, and we just ended at 6 p.m. Like that's not good. So we'll meet on Monday. We'll take some questions. We'll do some practice, and then you'll have Tuesday and Wednesday to work on the final.
Okay.
So the final is going to be open on Tuesday?
Yep. Yeah. I want to give you plenty of time to work on it. Yep. So I'll have it ready to go, posted Tuesday morning, And then you can have all of Tuesday and Wednesday. Because what I don't want is I don't want you to be in a situation where all of your teachers say, oh, well, we'll just have class all the way through Tuesday, and then Wednesday I'll post the exam.
Quick
You know,
question.
that would suck.
Mine is kind of a specific question, and it's more of on a personal level. But I just found out today that one of my coworkers, who I usually sit next to, has COVID-19. If I contract it and I am unable to do a test, is there any way I can?
Yes.
Do I email you or?
Yeah, and we would just do it incomplete, and we'd figure it out. We'd put a deadline. You know, you'd have to take the final by July or something.
Yeah, I just found out about that today. I mean, he hasn't been to work. He's my friend too. He hasn't been to work since like already 10 days, and I know the incubation period is about 5. So
it's a little, it's scary though. Yeah, but it's
I know,
for sure.
With my, I'm not scared for myself. I'm scared for my kids. I don't want to, I don't want to get them sick. But I think I'm safe now that like I said, the symptoms show up after 5 days. So
yeah, no, but we would just if something happens like that, and something for anybody else too, if something happens, we would just give you an incomplete and then coordinate finishing out the course. I think you usually have like 3 months. It's kind of we would sign an agreement that you would complete the assessments by whatever date, and
okay,
yeah,
all right. Just
totally.
Sure.
We'll take care of that if that happens. But that it won't happen. We'll stay positive. Okay, so back to the questions here. Let's see. We only have a half hour left, so let's pick another one here. I think 31 looks kind of interesting here. I didn't do this one in my other class. This looks interesting. Oh, okay. So here we have a cylinder. Whoa, what? I keep doing this here. I keep like touching the screen and suddenly it zooms on me. So I think I have somehow I'm not in the right form for I'm still getting used to this new tablet too. So we have a cylinder given to us. They even give it to us in cylindrical coordinates as a dead giveaway. So that's our cylinder, but its density is not constant. Its density depends on R. And in fact, as R gets bigger, as you move away from the center, you see what happens to the density? And it's getting smaller. Yeah, it decreases. So this is like dense in the middle, or it's like when R is 0, the density is 5, whatever those units are, 5 kilograms per cubic centimeter or whatever, whatever it is, it's some mass per volume. And then as you extend out away from the center, it gets less dense. It's less dense. So I'm going to draw the region here that we're integrating over. Solid cylinder, radius is from 0 to 3. We'll pretend that looks like a circle, 3. And then Z is from 0 to 2. So we'll just draw another one up here. Up at 2. So it's my attempt there to draw a cylinder, height of 2, radius of 3. And this is actually the section that we are going to skip, is basically this topic. So it's the idea of a center of mass, but the thing that I think is most interesting from there is finding the mass of an object. And so all it is, if you think of mass, if you have density, mass is just the density, the mass density that you have times the volume. So if you're thinking of the mass of our small little piece, delta M, that would just be the density multiplied by delta V, the volume of the small piece. And so the full mass, you just add them all up, density times delta V, and so it's just a triple integral. The point here is it's just a triple integral over the volume of the density dV. And that's the mass of the object. So let's see if we can set that up here. Triple integral, the density is 5e to the negative r squared. And then we have dz r dr d theta. Oh, this one is a solid cylinder is perfect for cylindrical. Why don't you take 15 seconds, because that's all it should take. See if you can fill up the bounds for that integral. Don't say it out loud. Don't unmute yourself. 15 seconds. See if you can fill up the bounds for that integral. If you're making it hard, you're making it too hard.
This one's too simple.
It should all be simple. Is there anybody who wants to chime in here, maybe with the Z's? Somebody we haven't heard from? Got some people lurking in the background, which is fine. But anybody want to type in the chat what the Z bounds are? Maybe Efren or Jeff, Kenny, Boy, Devakar. We haven't heard from any of you. Anybody want to contribute? 0 to 2 from Boy. Yep, very good. 0 to 2, excellent. Kenny's got it too. Yep, 0 to 2, excellent. And then the DR. How about somebody else? What would that one be? Jeff's got that one, 0 to 3, excellent. And then I'll do the d theta. We go all the way around, right? So that one's 0 to 2 pi. So a cylinder in cylindrical coordinates is the easiest. Easy limits there. Any questions on setting that one up? Okay. Not seeing any, so let's go ahead and do this one. Let's see, we've got triple integral 0 to 2 pi, 0 to 3. We're going to integrate z, so it's going to be 5r e to the negative r squared. I put the r from the dv with that. And then it's z from 0 to 2, dr d theta. So that'll give me an extra 2. So now I've got 10r e to the negative r squared dr d theta. Might be worth doing the U-substitution here. Depends on how good you are at that. U is negative r squared, du is negative 2r dr. We have 2r dr, we don't have the negative. So negative du will be r dr. And I'm going to do u, change my bounds. U at 0 will be 0, and u at 3 will be negative 9.
Okay, this is a dumb question, but how do you get u at 3 equals negative 9? You explained this before, but.
Yeah, so if we're doing the u substitution, u is negative r squared. What I'm doing is just substituting in the bounds for r. Just because u is really just a function of r.
Oh, okay.
Yeah, that's all.
All right.
Mm-hmm. Yeah. Yep. Yeah, it's just evaluating the function. Okay, so 0 to 2 pi, now it becomes 0 to negative 9. And then we stole a 2. It's 5, and then e to the u, because we stole a 2 for the du, and then it's negative du d theta. I feel like I always underestimate how much workspace this whole thing will take. But then I then I go ahead and have all this empty white space over here. Put you over there. Put you up here. Put you down here. See if this is enough. And put you up here. Okay, let's see if that's enough to squeeze it in here. Whoops, I gotta go back to drawing. 0 to 2 pi, negative 5 e to the u from 0 to negative 9, d theta. And so let's see, 0 to 2 pi, negative 5 e to the negative 9 minus e to the 0, which will be 1 d theta. And I'm just going to write this -5 e to the -9 minus 1, but then we get theta from 0 to 2 pi, and so we just end up multiplying by 2 pi.
Can you factor out the e to -9 out?
Yeah, there's a bunch of different stuff you could do there for sure. Yeah, I'm not really too worried about that. I was tempted also. Here I have the integral that seems to go backwards. It goes from 0 to -9. So it seems to go backwards. So I kind of want to switch it from -9 to 0. And then there's a negative sign there. So you could make it positive from -9 to 0. There's all kinds of different stuff you can do there. Not a huge deal. I keep looking up and waiting for someone to click the go slower again. We had somebody do it earlier. I'm like, oh, yep, sorry. So I'm trying to keep my eye on and look to see if anybody does it again, so I know. Let's see if we can set up 31. What time is it? 5:45. What's left? We have 31. Ooh, that looks cool. 43 looks cool. Oh, tough choices. Let's do the hard ones at the end. Let's do 43 and 44. Let's focus on setting them up. Okay, let's focus on setting up these integrals. Here we have a function. In 43, we have a function x squared plus, it's 1 over x squared plus y squared plus z squared, that all to the 3 halves. And we're integrating over the region that's the solid between the spheres of radius 1 and 2, centered at the origin. So clearly here, we should be using spherical coordinates. If you want to draw the region, it's kind of hard. If you look at it from the side, say we're looking at maybe like the xy plane here and the z-axis. There's a sphere of radius 2 and a sphere of radius 1, and we're looking at the between those. So what we really have is kind of like a hollow ball. It's not totally hollow. It's a ball with a hole in it, a ball with a hollow center maybe. So I was thinking like, oh, it's like a tennis ball, but like a tennis ball with a really thick wall, right? It's not just a thin wall, it's a really thick wall, and there's a hole in the middle. So in spherical coordinates, this is actually very simple. We have dv, we're gonna do, what is it, rho squared sine phi d rho d phi d theta. And then x squared plus y squared plus z squared is rho squared to the 3 halves. And then anything involving a sphere, the bounds are really simple. Just like the previous cylinder, the bounds are really simple. The sphere is really simple too. Why don't you see if you can set up the bounds there? I'll give you like 15 seconds again to work on that.
Is it 1 or 2?
For which one? The innermost one? For rho?
Yeah.
Yeah.
I think.
Mm-hmm. Yep. Right, because you're going from one sphere out to the next one. And then phi remember, is from the positive z-axis down. I think I'm reversed, maybe this way. I don't know. I can't tell which way it's flipped. One time I thought it was flipped, and so, but then it like really wasn't flipped when you were looking at it. I don't know. So yeah, phi would go, it needs to go all the way around. It needs to start up here and then rotate all the way down to pi. So 0 to pi for phi, and then we need to get all the way around the whole sphere. And so theta would go from 0 to 2 pi.
And phi is always supposed to be positive, right?
Correct. That's correct. If we look at the notes there, the definition of phi is it's a positive angle between 0 and pi. And rho is also positive. Now, it seems a little arbitrary because you can imagine a point over here that has maybe, it has a phi going down, but then maybe theta is all the way over here, and then rho is negative. But the definition is that rho is always positive. So rho is positive, phi is positive, theta is from 0 to 2 pi. It's kind of arbitrary, but it makes the coordinate system make more sense that way. If you define it that way, then it's arbitrary. It's a totally made up coordinate system. All coordinate systems are just made up. Like, why does x start at negative and go to positive? Because the countries where that was developed, it was the Cartesian coordinate system. René Descartes, French is written left to right. I mean, I don't know. There's no reason if it was developed in a country that was written right to left, then maybe everything would be right to left instead. It's totally arbitrary. So it just makes more sense if we have rho as positive and phi as positive. Any other questions on the setup there?
So in spherical coordinates, dv would equal rho squared sine phi, yeah, all that.
Correct. Yep. So there's three, kind of when we were doing the dA, we had the two options for dA, the area. For double integrals, you can either have the dy dx or the r dr d theta. dv has three options. You can have some combination of dz, dy, dx. So there's actually 6 different orders there, depending on your order. Or you could have dz, r, dr, d theta, which is basically just polar coordinates. That's cylindrical, though, technically in 3 dimensions. Or you can have rho squared sine phi d rho d phi d theta. And the derivation of that was in the notes. It's not trivial why it's rho squared sine phi. There's a visual that was in a textbook that it's an open source text. I was going to say I stole it, but it's open source. They want you to use it. But trying to explain why, where'd it go? Where those parts came from. Here it is. Nope, that's cylindrical, spherical. So this drawing kind of explains where the rho squared sine phi d rho d phi d theta comes from. Okay, good. Any other questions? Okay. We are coming up on only 10 minutes left, so let's try to set up this last one here. This looks harder. Maybe I'm just intimidated by the shape. It's not a sphere. It's got like some 4 secant phi. The heck is that in there? So I guess actually this one isn't that hard because I mean, maybe
it's intimidating.
It looks intimidating, but we don't need to write the integral. The integral is already written for us. I wish that they had given the description and asked us to write the integral for it. That seems more interesting. See, because here this is z equals 4. Right? That's z equals 4. And then do you see this cone at an angle of pi over 3? Well, that's the equation phi equals pi over 3. And you can see on the integral, theta is going from 0 to 2 pi all the way around. Phi is going from 0 to pi over 3. Okay. And then rho, if you imagine your little piece here is awkward. It has to go from the origin out to the top here. So rho starts at 0 and goes out to that plane. But just like circles are easy in spherical coordinates and polar coordinates, so spheres in spherical coordinates, circles in polar coordinates are easy, planes are not. And vertical lines in polar coordinates are very awkward. So I'd like us to at least investigate how did they get that? And it goes from the definition, and you should have this on your note card or your note page. You should have the definition of spherical coordinates. And if we go up here, we see that z is equal to rho cosine phi. Z is equal to rho cosine phi. Oops. Rho cosine phi. Well, that's constant. That's 4. What we need to know where rho starts and ends. So this is like one of those other equations. Remember, we had to do some where we had to solve for x, or we had to solve for z or something. So here we need to solve for rho. So rho is equal to 4 over cosine phi, and so rho is 4 secant phi. And that's where that upper limit on the integral came from. So rho is going from the origin out to the plane z equals 4, which is when rho equals 4 secant phi. And then again, phi goes from 0 to pi over 3, and then theta goes from 0 to 2 pi all the way around. So I think that was interesting just to discuss the bounds there, to kind of know where those came from. I don't think the integral itself, oh, maybe, I don't know, let's try. It sounds like it starts off pretty innocently because we're just integrating rho first. So that would be 1/3 rho cubed from 0, but then it's like, oh, 0 to 4 secant phi. Yuck. And then we still have times sine phi d phi d theta. So again, it starts off innocent, like, hey, just integrate rho. It's 1/3. We integrate rho squared. It's 1/3 rho cubed. That's fine. Oh, by the way, your upper bound is a secant function. So that's going to be 1/3 times 64 secant cubed phi minus 0, I guess. So just that times sine phi d theta. I think I know how to do this. 64/3 integral 0 to 2 pi integral 0 to pi over 3 secant cubed phi sine phi d theta. You're going to be able to do the d theta, so let's end the class on just this indefinite integral. Secant squared phi, secant cubed phi sine phi d phi. This is where, like, do you ever speak math? It's a really good skill to do that. And I pause sometimes and I say things like d phi, and I just have, it's like, you just sound silly. Like, who says that? Like, who says that? And it's hard because, like, then we're making fun of Greek letters. It's just a letter in the Greek alphabet. It literally is like saying like dp, like it's a letter, but it just sounds silly. Sounds silly to Americans. Okay, so Calc 2, trig integral. Not one of the easy trig integrals. Well, I don't know. Maybe. I don't know.
Would you separate the secant cube to secant squared minus 1 times secant?
I would not.
No.
No, I would not. I tell you what I would do. And this only comes with practice. I have taught Calc 2 many times. So that one I have a little more practice with. I'm going to pull off one of the secants and write it as one of a cosine.
I was thinking about what is a tangent? Secant squared minus 1, one of those.
Yeah, not a bad thought. Like, you definitely did some integrals like that in Calc 2. You definitely did. It's just not going to help us here. The problem we have here is all of our trig derivatives are either sines and cosines or secants and tangents, not secants and sines. So we need to convert them so they're either all sines and cosines or all secants and tangents. So my choice is to take one of the secants, write it as 1 over cosine, and then I have secant squared phi times tangent phi d phi.
And then this is just a U-sub, right?
Yes, what's your U, Jacob?
U would be tangent phi, and then D would be secant squared phi.
Yeah, you could actually go either way.
Really?
That's fine. It's totally fine to go U as tangent. You could also do U as secant.
Oh, and then you have secant tangent.
Secant tangent. So either one. you're actually safe either way here. So we will have the integral of u du. You might wonder how that works, like how is that possible? I don't know how much time we have left, but it's because, to Christian's point, there's a 1 minus. So they're off by just a constant, but you have a constant. And so your plus c covers that 1 minus in there, or that plus 1, or whatever it is. So that covers that constant. So that's how it works, how they would both work, and they would actually be equivalent. So that's the indefinite integral, and then of course we need to evaluate it from 0 to pi over 3 and all that stuff. I feel like most double and triple integrals, the challenge is, can you keep yourself organized? It's usually not challenging integrals themselves. Like this one seems to be harder than some of the other ones that we've done, except the quiz one. That was a bad one. So, but most of the time, the integrals themselves are not that bad. It's all about like record keeping. Can you keep yourself organized? Do you know what you're integrating now? Do you have your bounds noted correctly? Like that, to me, seems to be the biggest challenge on those. So I'm going to stop here. It's 6 p.m. I know you have other things to do. I'm getting hungry. So, but I think this was good. I hope you don't mind staying extra. I know if you have to go, I won't be offended, but I like the 2 hours. I think like we were really shortchanging you, going from 2 days a week down to, hey, here's a bunch of videos and we're going to meet for an hour and a half. It didn't feel like enough to me. I think this felt good. So I hope that's okay. But I will be here for 3 hours the last 3 weeks, and I think this is going to work out well. Any last questions before we sign off for today? All right, I'm not seeing any. So email me if you have any questions, you want anything to ask questions about homework or anything. I'm going to post the quiz. I have it on my list of things to do. I have to do it tonight because I forgot to write it earlier. So I'm going to post a quiz tomorrow morning on 16.3, 16.4, 16.5. That's double integrals in polar coordinates, triple integrals, and then triple integrals in cylindrical and spherical. So we'll have, again, probably just 1 question from each section. 3 questions is usually enough for our quizzes, so it should be plenty. Okay, that's it. Enjoy your Wednesday evening, and we'll see you again next week.
Thank you. Bye.
Thanks.
Thanks, Carmela. Bye. Bye, Jacob. Bye, everybody.